Good morning, all. In our last lecture, we discussed about query optimization, that is heuristics based query optimization, and we have seen an example of optimized query tree generation from an SQL statement. Actually, what we have done there was a series of operations moving down the select operation, joining Cartesian product and Cartesian product select operation, and many different types of operations, that is rearranging the different operation in algebra. We have obtained an optimized query tree from an initial query tree through a series of query tree, intermediate query trees. We reached a final optimized query tree. From the final query tree, you can write an optimized query relational algebraic expression also. Now, today's class, what we are going to see is general transformation rules for relational algebra operation. Actually in that example, we applied the rule. Actually, all are rule based optimization, rule based in the heuristics rules that we are applying. Today we will see what are the different rules. Cascade of select operation. A conjunctive selection condition can be broken into a cascade or sequence of individual select operation. For example, if our condition is like this: select C1 and C2 up to Cn, a condition contain n number of condition, then you can apply the last condition on relation, resultant relation. To the resultant relation, you can apply the next condition, and so on. That is what possible. As an example, you can see that if a condition contains salary greater than 50,000 and city is equal to Trivandrum, that is a conjunctive condition having two sub conditions. We can apply city first on employee. This condition, select city is equal to Trivandrum. Therefore, resulting relation will be having lesser number of tuples when compared to the original one. You can apply the second condition on that one. This is a first rule that can apply. Okay. Second is commutativity of sigma. This simple rule: sigma C1 followed sigma C1, then sigma C2 of R can be written as this condition can be sigma is commutative. Therefore, that is what simple rule. Third rule is cascade of pi operation. A cascade of similar to cascade of sigma, cascade of pi. That is, if you apply a sequence of project operation, then what is the result? The result is the last pi. Select project means you are only selecting a subset of attribute. Therefore, whatever you select, the final subset is only valid one. For example, the rule says list 1, list 2, list n. First you apply list n, last one list 1. Therefore, what the result should contain only. Therefore, you can replace this set of pi operation, sequence of pi operation, with a single pi operation or single project operation. That is, let be employee. First you project name, city, address. Next project is name, city. Next is name. Why? It's only just name. Single project operation is sufficient. Three rules we have seen: cascade of sigma or cascade of select, commutativity of select, cascade of project. Commuting sigma with or project select with pi or project select with project. Selection condition C involves. That is why here the question is whether a sigma followed by a pi can be written as a pi followed by a sigma, or a select followed by a project can be written as a project followed by a select. This is possible only if the condition involves, that is, a select condition involves attribute a1, a2, an in the project list, then this operation can be computed. Otherwise, it is not. That is, here the question is project of a1, a2, an followed by a sigma of or a select of C on R. That is, condition is applied on R, then a project. Is it possible to write a select of C followed by pi 1? This is possible only if the condition that the C contains or the condition contain only the attribute from a1, a2, an. From this list only, then only it is possible. For example, here this is a salary greater than 50,000 is a condition to be applied, and this is the resultant relations attribute: name, department, address, and salary. You are going to move this pi or the project to inside. Then this is possible only if the salary is also project. Otherwise, when you apply the condition, he cannot apply the condition because that will not be a valid statement. Here this is name, department, select salary. This attribute list contain those attributes which are involved in the select condition. That is why it is possible. If the salary was not projected, then this would be a wrong statement. Fourth condition, commuting sigma with pi. Then commutativity of join, as similar to cross product. The same rule is applicable to cross product also. Join, join operation is commutative, as that is R join on conditional join with S can be written as S conditional join with R. Similarly for cross product also, R cross product S can be written as S cross product, same result, no problem. Sixth rule is commuting select and select with join. Commuting select with join, that is a select followed by a join can be written something like this. If all the attributes of the select condition C involve only the attribute of one of the relation being joined, say R, the two operation can be commuted as follows. That is, here the operation is like this. Here what is this? Select C is a condition, R join S. You can move this select into R if the all the attribute in the C is belonging to the relation R, or if all the attributes belong to S, then we can apply this select condition to S also. Here you assume that all the attributes are that of all the attribute of C are that of R, then you can write sigma of C first. So you can do the select first, then if you do the select first means you are reducing the number of tuple in the resulting relation. There a smaller relation is joined with the other relation S. Therefore, this is computationally giving you an easier mechanism by selecting first, or by applying the select operation first. For example, this is the case, that is, you join and after applying the select condition you can move this condition inside. That is, you apply the salary greater than 50,000. Those employees with salary greater than 50,000 will only be selected, and with that resultant relation you are applying this. This is a rule number 6. This is an optimization technique that we normally apply. All the rules are for heuristic or optimization. Then alternatively, if the select condition C can be written as C1 and C2, where C1 involves only attribute of R and C2 involves only attribute of S. That is, here the condition is like the condition contain two sub conditions, C1 and C2, and C1 contain attribute belonging to R and C2 contain attribute belonging to S. You can write like this, sigma C of R join S. That is, here after joining then you apply the condition. The condition contains C1 as well as C2. In that case you can write sigma of C1 into that is, the sub condition is applied on R and sub condition is applied on S. The resultant two relations are joined. Therefore, this is more computationally easy one. The next is commuting project and sigma. Earlier in the rule 6 was commuting select with the join. Now commuting project with the join. Suppose that the project list L contain A1, A2, AN and B1, B2, BM, where A1, A2, AN are attribute of R and B1, B2, B are attribute of S. If the join condition C involved only attribute in L, two operation can be commuted as follows. Here also the question is, you have a project with this project L and R in this R join S. Whether you can apply that project of this first A1, A2, AN on R, then project of B1, B2, BN on S, and then perform the join operation. This can be done only if that condition and if the join condition C involves only attributes in L. That is, if R join conditional join S pi of L, then this can be written as pi of A1, A2, AL on R join this. That is, you perform the project operation first on both relations and then you are combining. then the C must have only the attribute in this projected list. If some more attributes are there, then for example the C involves some other attribute like a n plus 1 up to a n plus k, then what you have to do is when you project from the relation R, then you have to include that additional attribute that is part of the condition. That is project a1 up to an and a n plus 1 up to a n k. These are the additional set of attributes that is there in the condition. For both relation you can do that one, that is project b1 b2 bm and a1 plus 1 to an let bp. These are the additional attribute that is coming. Then you perform, after projecting this you do the join operation on the condition. The condition involves some additional set of attributes, that is a1 other than this. This is also commutating project and join. 8th is commutativity of set operation. Set operation union as well as intersection is commutative, but minus the difference is not. That is R intersection S can be written as S intersection R, no problem, but R minus S is not S minus R. That is what it is says. Associativity of join, Cartesian product, union and index. These four operations are individually associative. That is theta stands for any one of these four operations. Then we have, for example, R join S join T can be written as R join S join T. That is, this is done first, followed by this. This associativity is true for join, true for, that is you must apply only a single operation at a time. That is, here if it is R Cartesian product S Cartesian product T can be written as R Cartesian product S Cartesian product T. That is what possible. Similarly, union as well as intersection, this rule is associative. Commuting select with set operation. Select operation commute with union, intersection and set difference. If theta stands for any of these operation, we can write like this. If sigma or the select of C R theta S, theta means union, intersection or a single operation at a time. For example, R union S on this condition can be apply this condition first, then apply this one. Similar to this we have seen in other join, etc. The same rule is applicable here. The pi operator, the project operation commute with union. Pi L R union S is equal to pi L union pi L of S. That is commutative of union also. Converting a sigma and cross product, that is select and cross product. This we already seen the example also. We have done this one in when we solved that example. That is select followed by Cartesian product is actually join. Therefore, whenever there is a condition, select condition followed by a select operation is applied on a Cartesian product of result of Cartesian product of R and S, then this entire thing can be replaced with a join on condition C. This is selected and join on condition C. These are the 12 rules, heuristic rules that can apply so as to from the initial query tree. These rules whichever is applicable apply, and final query tree can be. Therefore, there is a algorithm outline of heuristic optimization algorithm. Using rule 1, break up any of the select operation with conjunctive condition into cascade of select operation. That is the initial query tree. You know the relations are joined or clubbed together with Cartesian product, and whatever condition the where clause is written in the with a select condition, with a combined condition, a conjunctive condition. Therefore, break that conjunctive condition into individual operations, cascade of select operations. That is what, because select followed by a project operation, that was in the initial query tree. That is Cartesian product of all the relations followed by next intermediate node was a select operation on whatever the condition that we specify in the where clause of SQL statement. Now this select operation with so many conjunctive condition, you break that one and uh, apply cascade of select, that break into separate set of select operations. Using rule 2, 4, 6, 10 concerning the commutativity of select with other operations, move each select operation as far down the query tree as is permitted by the attribute involved in the select conditions. You please go back to your original example, where what you have done is you move the select into the tree path wherever it is possible. For example, select salary greater than 50,000 that belongs to employee relation, then you can move that condition, select condition, down to the leaf node, where just above the leaf node, to that condition. Similarly, by applying rule 10, or for example rule 6, you can see what is rule 6 says. Rule 6 says something like this, that is commuting sigma with join. That is, wherever this condition is there, we can apply this select condition into this relation R. Similarly, rule 10, rule 2, etc. says like this. You can apply this rule. That is, you first apply the select condition, resulting relation, other relations, other conditions are. This is applicable to the cross product also. That is what. Next is using rule 9 concerning the associativity of binary operations, rearrange the leaf nodes of the tree so that the leaf node relation with the most restrictive select conditions are executed first in the query tree representation. Please go back to your original example. There what we have done is the employee as well as project on a select condition on project relation, that is project sigma of accuracy or something, that returns only a single tuple, whereas the salary greater than something, or employee some condition, oh sorry, birth date greater than this one, on employee. These two relations we sapped in the leaf nodes of the original intermediate tree. We sapped some of the two relations, employee as well as project. What the rule we applied is the associativity of binary operation. That is, rule 9 states like this. Associative, these operations can be that in the relation, the leaf nodes can be moved down or up. What is the objective here is those relations, when the condition is applied, which returns lesser number of tuple, that is moved down. That is what rule 3 says, or algorithm 3 rule step 3 says like that. Using rule 12, combine Cartesian product operation with a subsequent select operation in the tree to join. That is, we already discussed this one. That is, rule says like this: select a Cartesian product of two R and S Cartesian product. On the result of that one, if you apply a select operation, that is equivalent to a join operation. Replace those Cartesian product and select with a single join operation. Similarly, using rule 3, 4, 7, 11 concerning the cascading of project and commuting of project with other operation, break down and move the list of project down to the tree as far as possible by creating new project operation as needed. In our original example, we have seen that in the final query tree, we moved all the project operation. We inserted some of the project, not moved, inserted some of the project operation. That means we applied only those attributes which are required. That is what we have done. That is, you can move the by applying the operation, you can move down all the project operation down the tree. Identify subtree that represent group of operation that can be executed in a single algorithm. That is the final step. By applying these rules, all the rules or some of the rules from on the initial query tree, you can generate a final query, optimized final query tree. From the final query tree, you can write the resultant algebraic expression, which will be a more optimized one. Therefore, with this we complete the chapter, the module 5. There's one more module is left with us.